At 5:56 p.m. local time on Monday, January 19, 2026, a magnitude 4.9 earthquake struck South California. Due to its location, specifically occurring around 12 miles north of the city of Indio, the resulting several seconds of ground motion was felt by more than 10 million people, with some feeling it as far away as Los Angeles, Barstow, or Mexicali across the border in Mexico. Thankfully, this caused no damage, with maximum shaking in an inhabited location being equivalent to this simulation. Here are the current stated odds for aftershocks to occur in various stated timeframes, but these are statistical averages and not a true prediction since earthquakes cannot be predicted. While the 4.9 quake that struck was seemingly unremarkable, the light earthquake was scientifically interesting for a number of reasons which I will outline. Normally, aftershocks following a main shock earthquake tend to follow a 1/x rate if x represents time since the main shock, decreasing in abundance following that formula. However, the actual rate of aftershocks from this quake was notably higher than this, specifically more than 250 separate detectable aftershocks, with many occurring at a much higher rate during the first 10 hours than would normally be expected. This made it initially seem like an earthquake swarm. Yet, it is not one, as instead, these just happen to be a temporary 50 to 200% higher rate of aftershocks for a time, but there still was an overall declining rate of events. In other words, still somewhat following the expected number of aftershocks. But what about the earthquake itself? Why did it occur? The moment tensor showing the top-down view of fault movement from the 4.9 earthquake shows the earthquake occurred on oblique fault, specifically a normal right lateral strike slip fault, almost as if two different stress sources were acting upon this fault. Now, this is a bit interesting because no known and mapped faults by the US Geological Survey follow that orientation. However, the key word is mapped faults. Plenty of smaller fault lines exist, and this particular section of the desert has an absurdly high number of visible lineaments in the exposed rock formations. While not all of these lineaments I labeled are indeed fault lines, they regardless still give a decent indication of regional tectonic stresses. I personally interpret that the 4.9 earthquake occurred on one of these four possible faults, and these parallel the general distribution for the main cluster of aftershocks. Many of the magnitude 2.5 or larger aftershocks even occurred on lineaments after I mapped them. However, there were also a secondary cluster of earthquakes 1.3 miles to the southwest, which was related to a similarly trending fault line that produced a magnitude 3.2 quake 4 hours after the 4.9 quake. And these faults in turn parallel a series of more distant faults such as the Johnston Valley Fault Zone, the Burnt Mountain Fault Zone, and the Coachella Fan Fault Zone. All of these sort of are branching faults occurring at the approximately same angle off of the major San Andreas Fault. Thus, the recent earthquakes could be said to represent a combination of regional strain from being at the very edge of the Basin and Range province, hence extension, combined with strain associated with the San Andreas Fault. Larger earthquakes have occurred on similarly trending regional faults to the north somewhat recently, such as at the Lavick Lake Fault in 1999 and 2008, and an unnamed fault 12 miles east-northeast of Barstow in 1997. Overall, an earthquake of magnitude 4.9 or stronger has struck beneath the landmass of California 84 times in the last 30 years, translating to an average rate of 2.8 such events a year. Thus, the recent quake isn't truly rare in terms of its size. I hope that you found today's video interesting. As a final note, I would like to thank this channel's patrons on Patreon and channel members on YouTube for supporting my work.